Okay, so where we left off, we were saying to calculate the pKa incorporating the pH values that were determined by Nannerl's experiment. Okay, so basically the equation we're now going to focus on to determine the Ka and pKa, this one here. Okay, so we're going to basically do them individually. So the first one is that the Ka equals the concentration of the proton times concentration of the A minus divided by the concentration of the associated acid. Okay, so the first thing we're going to work out is the concentration of the H plus. And that will equal the, basically, that equation there. Okay, so we're going to use the experimental values of Nannerl's there. Okay, so if we plug those values into my trusty calculator, you'll get 4.16. It'll be 0.92 times 10 to the negative 5. Okay, obviously I'm rounding because it makes the maths easier for me, but in exam situations, just keep those numbers until the end. Okay? And now we use the equation. So Ka will equal the 6.92 times 10 to the negative 5 times the ratio. Okay, and you'll get the ratio, of course, from your table. So it'll be 0.33, which equals 6.92 times 10 to the negative 5 times 0.333 reoccurring. So it'll be 2.31 times 10 to the negative 5. Okay, and that's what we put in that first value there too. 2.31 times 10 to the negative 5. Okay, so that's the example for example 1. So now let's do example 2, because obviously the proton concentration is going to change because the pH changed. So the concentration again of H plus will equal 10 minus, this time it'll be 4.60. So that will equal, again, getting the old calculator out, minus 4.60, 2.51 times 10 to the negative 5. Okay, and the Ka will equal 2.51 times 10 to the negative 5, because if you, and times 0.98. Now, ideally, of course, at half neutralization, that value should be 1, but it appears, due to the difference in concentrations of the acid and the associated base, it was slightly off. Okay, so we just times that by 0.98, so it'll be 2.46 times 10 to the negative 5. Okay, so it will be 2.46 times 10 to the negative 5. Okay, the numbers, they're kind of matching. Okay, that's a good sign. Okay, so that's the second example. And the final example for our average, of course, we do things at least in triplicate. For IAs, I'm expecting about 5. Okay, so it'll be 10. Let's be consistent. Concentration of the protons will equal 10 to the negative 4.88, which equals 1.33 times 10 to the negative 5. Okay, and the Ka will equal 1.33 times 10 to the negative 5 multiplied by the number 2.93 from our values, which will equal, was a bit high, that one, 3.8, 8 cell, never well done, 3.86 times 10 to the negative 5. Okay, so that's a bit on the higher side, but that's what we get. Negative 5. Okay, so now we're just going to take the average. The average will equal, once I calculate it, okay, divided by 3, 2.88 times 10 to the negative 5. Okay, so that's our average using that number. Compare that to 3.74 times 10 to the negative 6 for the equilibrium method. So there's definitely a disparity between the two, and you should comment about the associated accuracy and precision of those two methods. So I'm just going to convert that to a pKa. Okay, so pKa will basically be negative log base 10 of that number, or Ka, which equals, if we again get the calculator out, 2.88 times 10 to the negative 5. Okay, so that should be about 4.65. Okay, so if we look at our tables in our data booklet, you'll see that corresponds to the pKa of ethanoic acid or vinegar, which is what you should have determined as a class that the acid was. Okay, so that's pretty much how you do the determination of Ka, both from the equilibrium method and for the partial neutralization method, and you can probably determine which is more precise.